Okay, question 22. This question is about we've been provided with some data and we're going to do a bit of analysis of them. So what they've done is they've got some springs in parallel. So here they've got two springs in parallel and they've applied a weight of 0.8 newtons. They've measured the extension of the springs, and then they've done that for 4 springs in parallel, and then 6 springs, and then 8 springs. Not relevant for this question in particular, but more generally, remember, if we wanted to get a good set of data, we probably would have wanted to do at least 5 different values, and also done some repeats for the extension and taken a mean. We're not assessing that in this question, but more generally, that would be best practice for doing that. So the first question, explain why the student found it difficult to measure the extension shown in the table. Well, basically, they haven't put enough weight on here, so the extensions are very small, okay, particularly once you get down to, you can see the more springs there are, the lower the extension is. So if the extension is only changing by 0.1 of a centimetre, that's basically a millimetre, well, that's the smallest value you can actually measure on a ruler. So it's going to be quite difficult to make those measurements and to be accurate. So how are we going to get the mark? Basically, the extensions are very small. Very small. And we can only measure to nearest millimetre with our ruler. Okay, so the next question is, how could we improve the experiment to produce extensions that are easier to measure? Well, basically we just need to apply a larger weight. So you could say larger mass or weight or force. That's given that they've labelled it as weight, let's say larger weight. To increase the extension. Okay. Right, the next part of the question is going to be to look at a graph. So we're going to look at the graph that they've plotted using this data. Okay, so here's the graph. And the first thing we've been asked to do, and sometimes students miss these questions. You're going through a paper and you're looking for the lines basically where you're going to put your answers. Okay. It's also really important just to keep an eye on sort of the marks available, because often it's quite easy to miss one of these kind of questions where you're doing work, say, on a graph, because there isn't a line to write your answer, because your answer is actually going onto the graph itself. Okay, so this is just an example of being really careful to make sure that you don't miss any questions out. So we've been asked to circle the incorrectly plotted point and then plot in the correct place. So basically you need to just go through each value in the table until you find one in the wrong place. And what you should find is the value for 4 springs should have been plotted at 0.4. The value for 4 springs should have been plotted at 0.6, and they've put it a little bit high. So that's the incorrect value, and actually it should just be there. And in I'd say it's a good idea. I haven't drawn that very well, have I? It's a good idea actually just to use your ruler to help you find the right spot on there. Okay. So that's the 2 marks for there. 1 mark for circling and 1 mark for the correct plot. And then the next thing we need to do is describe the relationship between the number of springs in parallel and their extension. Okay, so whenever you're describing a relationship like this, I would always start with saying and then whatever you've got on the x-axis. So in that case, it's the number of springs in parallel. So as the number of springs in parallel increases, so basically as we increase the number of springs here, the extension decreases. Okay, so as we increase the number of springs, you can see the extension is coming down along that line. So as the number of springs in parallel increases, the extension decreases. Now it's really important here that you don't get this statement the wrong way around. Okay, sometimes you see students saying, as the extension decreases, the number of springs in parallel increases. Okay, that's back to front. Okay, it's increasing the number of springs in parallel. That's your independent variable that's causing the change in the extension. Okay, so you always need to start with your independent variable, the thing that you're changing. Okay, you always need to say as the number of springs in parallel. That's the first part of your sentence. As that increases, what's the effect that has on the extension? That's causing the extension to decrease. Okay, so the independent variable, it should always form the first part of a description of a relationship. Okay, and then the dependent variable, the thing you measure, should always be the second part of that statement. So look, independent variable comes first. As you increase that, the dependent variable, the extension, decreases. Okay, we could do even better than that. That would get us the marks, but we could also say that the relationship is inversely proportional. Okay, as this one goes up, this one goes down. Okay, that's what we call inversely proportional. The extension is inversely proportional to the number of springs. Okay. The next question, you can see, again, really important to look at the number of marks available. We've got 5 marks here, so we've clearly got to do a little bit of work. Okay. We're going to end up, we're basically doing a calculation. Use the graph to calculate. So first of all, use the graph. We need to actually use the graph to get our values, and we're doing a calculation. Okay, so we're doing quens. So the first thing is, let's write out the quantities. We've been asked to calculate the spring constant. Okay, calculate the spring constant, that's one of our quantities for a single spring. Okay, so that's telling us where to look on the graph. And these are the quantities we're interested in, the force, the extension and the spring constant. That's what we're trying to find. Okay, so I'm just going to start by writing out my quantities that I know. So let's have a look. So first of all, we're going to get the extension from the graph. Okay, so the extension, when you have one spring, well, one spring would be here. They didn't actually try it with one spring, but we can use the line of best fit to estimate what the extension of one spring would have been. So if you find one down here, do a vertical line upwards with your ruler until you hit the line of best fit at 1.6 and then go across, and that is the sort of predicted extension for one spring. Okay, so we're getting a mark basically for reading the graph correctly, finding one spring in parallel, and then working out what the extension would have been predicted by our line of best fit. Okay, so let's write that down. So the extension equals 1.6 centimeters. Okay, let's do a quens. What else have we got? Well, we've got the force exerted by the spring, and we get that from the first part of the question over here. So we've been told already that it's got 0.8 newtons being exerted on it. So the force equals 0.8 newtons. And then the spring constant is our unknown. Okay, so that's our question mark. Next thing is we need to check the units, and this is where one of our 5 marks is coming from. And often if you've got a 5 marker, it probably means you're going to be changing units, okay, to justify why there's so many marks available. Okay, and we need to change our units here, because look, the spring constant's been given in newtons per metre, and our extension's in centimetres, so we've got to convert that into metres. Okay, so underneath I'm going to write extension, and you can use symbols for this to save you a bit of time, is equal to 0.016 metres. So you just divide that by 100. Okay, we've then got the equation, which is the force equals extension times spring constant. Then we'll put in our numbers. So 0.8 newtons is equal to 0.016 multiplied by the spring constant. And then finally, let's solve that. So the spring constant equals, we need to basically divide both sides by 0.016. So it's going to equal 0.8 divided by 0.016. And when you put that into your calculator, you should get 50 newtons per metre. Okay, so quite a lot to that question. We've got to get some values from the graph. We've also got to remember that the force we were given right at the beginning of the question, and we need to do a unit conversion. So that's why there's 5 marks available. Okay, last bit, just a 1 marker here. So a manufacturer is basically making a mattress, and they've got to explain, well, we've got to explain which of these mattresses would compress the most when you lie on it. Okay, so basically we're looking for the one with the lowest spring constant, because that's the one that requires the least force or the least weight on it to compress it. Okay, so that's going to be mattress spring R. The reason requires least force to compress, or another way of saying that is it has lowest spring constant. And that is question 22.